Bueno, buenas tardes a todos y todas. En primer lugar, quiero hacerles llegar el saludo de nuestra rectora de la Universidad Nacional de la Patagonia Austral, la profesora Roxana Puebla, quien nos pidió especialmente transmitir su acompañamiento en estas jornadas. Quisiera comenzar agradeciendo de manera muy especial al profesor doctor Ioannis Pitas por su visita y por compartir con nosotros la charla que tendremos a continuación, que además inaugura un hecho que seguramente los profes lo van a poder profundizar mucho más, un hecho muy significativo para nuestra institución, que es la incorporación de la Universidad Nacional de la Patagonia Austral a la AIDA. Para nuestra universidad es un paso muy importante formar parte de este conjunto de instituciones académicas internacionales y particularmente ser la primera universidad latinoamericana en integrarse a esta red. Sin lugar a dudas, la inteligencia artificial constituye hoy un área estratégica de desarrollo científico y tecnológico a nivel global, con un impacto transversal en múltiples disciplinas y sectores de la sociedad. En este contexto, la adhesión de la UMPA a AIDA se fundamenta en la necesidad de fortalecer nuestro posicionamiento institucional dentro de una red internacional de excelencia académica y de consolidar vínculos con instituciones líderes en formación e investigación en este campo. A través de alianzas de esta naturaleza buscamos generar instancias de cooperación académica e institucional que beneficien tanto a nuestros grupos de docentes e investigadores que trabajan en inteligencia artificial, como a la universidad en su conjunto. Entendemos que esta incorporación contribuirá al desarrollo conjunto de actividades de formación e investigación doctoral en inteligencia artificial junto a universidades de reconocida trayectoria internacional en el área. La red AIDA agrupa principalmente instituciones europeas y promueve estándares de excelencia en la formación de recursos humanos de alto nivel en inteligencia artificial. Esto abre oportunidades concretas en el fortalecimiento de nuestras capacidades institucionales de investigación y formación doctoral. La membresía en AIDA constituye, por lo tanto, un recurso institucional de carácter transversal que contribuirá a fortalecer las capacidades académicas y científicas de la UMPA. Finalmente, quiero agradecer a Daniel Pandolfi, al magíster Daniel Pandolfi y a la doctora Andrea Villagra por su compromiso y por las disertaciones que compartirán en estas jornadas. Muchas gracias. Quisiera, bueno, ahora le voy a dar la palabra a Andrea para que pueda hacer una presentación mucho más profunda del profesor y también aclararles o un poco invitarlos también tanto a la presentación de hoy, de agradecerle su participación por la presentación de hoy que va a realizar el profesor, e invitarlos para mañana también a las presentaciones, a las conferencias que van a dar Daniel y Andrea acá mismo a partir de las 16 horas. Algo importante que quiero aclarar para no olvidarme es que como el profesor va a hablar en inglés, les pido a la gente que está en Zoom que habilite los subtítulos para que puedan poder comprender, los que no saben inglés, poder comprender la presentación. Y a los que están acá presentes, los televisores van a tener la traducción abajo de la presentación. Son a modo de aclaración. Ahora sí, lo dejo con Andrea.
Muchas gracias. Bueno, muy buenas tardes, bienvenidos. Y nada, solamente decir que es un honor, ¿no?, recibir al profesor doctor Ioannis Pitas, IEEE Fellow y presidente de AIDA, International Artificial Intelligence Doctoral Academy. El profesor Pitas es investigador principal en la Universidad Aristóteles de Tesalónica, Grecia, con más de 980 publicaciones científicas y 39.400 citas a su trabajo. Actualmente coordina el proyecto Horizon Europe Tema, sobre análisis de grandes datos para gestión de desastres naturales. Como presidente de AIDA, lidera una red internacional de excelencia en educación e investigación en inteligencia artificial. Así que nada, bienvenido, profesor Pitas. Un aplauso para él y lo vamos a dejar acá.
Bien, vamos a darle la palabra al profe. Nosotras vamos a ir a ocupar otros lugares y todo suyo la presentación.
I would like to thank very much, Umpa, for giving me the opportunity to come here and also for your kind words. I don't understand Spanish, but I can understand kind of universal Latin. And in this sense, I understood more or less what you were talking about. So now let's move to the topic of my lecture, which is similarly very diverse. It's about AI, about complexity, life, environment, and so on. And you can wonder what's the relation of those two things, because apparently in your minds they can be unrelated. To understand what's going on, I'm going to start with some basic things that come from electrical engineering, computer science. It's about systems theory and networks. So these are the mathematical foundations that are needed to describe what I'm talking about. If you don't have this background, it's okay. You can, because my description is not going to be mathematical. My description is going to be qualitative. So more or less, you're going to understand what's going on. So let's start with systems, and systems are a basic tool for us understanding the world. We model the world this way. For example, if we have a box, we call this box system, and we have an input signal and an output signal. For example, my voice is input signal, and what you hear from the loudspeaker, it's the output signal. And in many processes that exist in the environment can be described this way. And there is a particular case where we have systems that are linear and time invariant. In this particular case, we describe them through a linear operation, which is the so-called convolution. Again, if you don't know mathematics, it doesn't really matter, because it's
recording
not that
in progress.
The important thing is that systems are a basic mathematical tool for modeling our world. The entire Earth, for example, is also a system in the sense that it receives solar radiation and then it emits heat in the universe. So in this sense, it's also a system. Unfortunately, most of the world systems are non-linear, but what we typically learn in the undergraduate studies in electrical engineering and computer science, it's linear systems because they are easier to understand, and they are very well coupled with linear algebra analysis and also probability theory, in particular Gaussian probabilities, and they create a general framework that combines mathematics with statistics, probabilities, and physics, and this is how we model our world these days. An important special type of system is the so-called feedback systems that we use for system control. For example, if we have a living organism and it has to survive to the environment, it has the so-called homeostasis. This means that when it receives a trigger, an input, then it reacts to this, and it reacts in such a way so that life is stable. Okay, this is a classical system control system in life, but all systems that are related to automatic control these days, they are mostly feedback systems as well. Our world is dynamical in the sense that it changes, and since it changes, then the primary tool for describing this is differential equations. Again, you need mathematics to understand what's going on. For example, if we have diffusion processes, when we get a drug and it enters into our stomach and then it goes into our blood, this is a diffusion process. When you have a new idea and you put it in somewhere in social media and it starts spreading around, this is also a diffusion process. Typically, such diffusion processes are described by differential equations. As I've told you, our world is dynamical because it changes, and in most cases it's nonlinear. So linear system theory is not really of big use in describing our world. It's our first approximation to understand the world. If we want to approximate it better, then somebody has to do a master's thesis study or even a PhD to study a particular process and model it properly in a nonlinear dynamic way. Because we have these issues in our world, then we observe chaotic behaviors and we have difficulties in analyzing our world. We are lucky because many processes that we observe or many things that we construct can be described by such input-output relations. For example, in neuroscience, let's suppose that by W I model the human brain, then X can be a visual stimulus, an image that we see, and Y here is the decision that we take. So this is a very abstract way to model how our brain works. And in the same way, we can model machine learning systems, artificial neural networks. In this particular case, an artificial neural network is described by a weight vector W. Let's suppose that this neural network does face recognition. It takes a picture of me as an input X, and then the output is 1 for me and 0 for the rest of you. And this is how the artificial neural network says that this is a picture of Peters, okay? We have, if we describe the world that we use differential equations, this is a difficult way to do, and it requires tremendous computational resources to analyze the world this way. So sometimes we resort to more static models to describe our world. Let's suppose, for example, that we have a social network and its nodes, these points here, this point here and that point there, they are people, and then they are linked by, let's say, friendship relations, okay? And now this is a network, social network in this particular case, and this describes social interactions, and it can be mathematically described by a graph. So you need graph theory to analyze social networks. And this is what is done nowadays when we do social media analytics, for example. Now, we have two different descriptions of the world, the dynamic one that is based on differential equations and the static one, which is based on graphs. And they don't reconcile that well to each other. Here, for example, you have the old Roman Empire and the roads that connected the various cities in the Roman Empire. That was a graph. And ideas like Christianity propagated along those graphs, those roads. On the other hand, here we have a physical system, continuous diffusion model, and this is described by differential equations. So it's difficult to, we have diffusion processes here in the network, and we have diffusion processes also in pharmacokinetics, for example. We cannot reconcile well those two worlds, even nowadays. So now, we observe that our world has a complexity that is ever increasing. And I'm going to argue on this because it's an unstoppable process. We don't know why this happens. It's an epistemological, let's say, question. Nevertheless, our world is complex, so we have to define its complexity mathematically. And the question is how you define, we define system complexity. It's not easy because we have several graph complexity measures, but none of them is universally acceptable. If we have dynamical systems, then, for example, recursive and feedback systems or chaotic systems, how we can model their complexity, it's a big question. There are, again, several theories on how to define complexity there, but there is no unique reply. And this is already bad enough, because when you have many different definitions, then you don't know what to choose from and what to use. And another issue is to measure functional complexity. For example, let's take our brain. Our brain is a biological system. It consists of millions of neurons that are interconnected. So it has an anatomical complexity. And then we have human intelligence, which is the output of our brain, which again is difficult to define. And then we have to measure functional complexity. What's the relation between the brain complexity, neural system complexity, and intelligence? When it comes to dynamical systems, we tend to associate complexity with regularity and randomness of such systems. So if we have a system that is completely ordered, like a crystal, for example, then this has low complexity. If we have a system that's purely random, it has low complexity as well. If we're somewhere here in between, then we say that we have a high systems complexity. Again, you see that this description is qualitative. It's not quantitative, and this creates problems, because if we want to do analysis, then we need specific and exact mathematical descriptions that we don't have. Let's take, for example, the case of the graphene atom grid. It's very regular, so its complexity is low. If we take the neural centers in the brain that are associated with speech, there are quite a few of them. They are connected in a certain way. They're not random. They're not regularly connected either. So we can say that this system has an increased complexity. So when it comes to network complexity, things are a little bit easier. We have various definitions on how to measure network complexity. And as I've told you, regular lattices or random graphs, they have low complexity. On the other hand, if we have scale-free networks that support the power law and small world networks, then they have high complexity. Social media are such a case. They are small world networks, social media, because in 5 hops, if I go from myself to a friend of mine, to another friend, then I can reach anybody in the world. So the diameter of the social media world is only 5 hops. And also in social media, you know that there are some influencers that have millions of followers, and then it's the rest of us that have only few followers. This means that the social media networks follow the power law, and they are scale-free networks, and so they're complex networks. There are ways to try and use information entropy as a measure of complexity. There was even an effort to use entropy to measure matter. There was an effort to measure matter entropy as well. However, these theories are debatable. There's no conclusion on this yet. And there are 2 aspects of entropy we have to take into account. One is probability entropy that you learn in courses on information theory, and then it's thermodynamical entropy, which is related to information entropy, but it's a different thing than you typically learn it in a course on thermodynamics. Now, as I've told you, we see that we have a complex world. We see this complexity being increased every day. It's an unstoppable process. And then we have many issues that we can associate with complexity. For example, we know that there's no life and there's no intelligence without complexity. So it's a necessary condition to have life and intelligence. We have to have a complex organization of matter. Whether it's sufficient or not, that's another story, because a Christian may say that just having a complex matter, it's not enough to have intelligence, it's not enough to have life, because where is the soul, for example, okay? So you see all these things that we discuss have also implications in philosophy and also in religion. And depending on your inclinations, then you can address these issues accordingly. And we observe that both living matter and our constructs and our society ever increases. In the past, we had huts, and then we had houses, then we had towns and high rises and very big cities. So this increases the complexity of our society, the complexity of our social mechanism increases tremendously. It increased tremendously due to social media, for example, just by themselves, by their existence. And the question is why this happens, and whether it can be stopped. Actually, it seems that it's against the second thermodynamic law. For the ones of you that know about physics, thermodynamics say that in the long run, the universe is going to die out of heat death. So everything is going to be mixed together with no regularity, and that's the end of the world. But we don't see this happening. So it seems that we are in contradiction with classical thermodynamics theory. So let's take things one by one. Let's start with matter. In matter, we have atoms. I don't want to talk about subatomic structures, because then this complicates things much better. But let's start with atoms, okay? So do you know that atoms are organized to get molecules? Why? Because we have bonds between the various atoms, and essentially by forming molecules, we minimize bond energy. So essentially, we create a more complex structure that has less free energy. And this continues because we have small molecules, like we have bigger molecules, then mega molecules, like in the case of very, very big protein chains. If you have this protein change and you allow the atoms to self-organize, then they do the so-called 3D protein folding, and they take a form that minimizes a certain energy. And this is stable, a stable situation. So by minimizing energy and increasing complexity, we achieve smaller energy levels. But formally speaking, there's no definition of matter complexity. Thermodynamic entropy is related to matter order and matter randomness, because randomness is a result of high thermodynamic entropy. If the matter is well organized, then it has low thermodynamic entropy. The second law of thermodynamics says that the total entropy of a closed system never decreases over time. However, some of the important systems that we have, they're not closed ones. It's not easy to have a closed system. Human Earth, for example, is not a closed system because it receives solar energy and then it radiates out heat. So it's not a closed system, and then the second law of thermodynamics does not apply. The inorganic matter complexity increases as we move towards equilibrium. There are some notions coming out of statistical physics that can be applied to this end. In physicists, for example, they define the action as the difference between kinetic and potential energy along a certain path of the evolution of a system. And the system follows such a transition path that extremizes action, actually minimizes action. So essentially, this extremization or minimization leads to more natural or stable paths. So by decreasing essentially energy, we enter into stability in that has more complex form. That's the general idea. But all these things, thermodynamics, statistical physics, and so on, we cannot just cherry pick ideas as I throw them to you right now. They have to be studied, specifically having in mind matter complexity, and this study has not been done yet. So it's a matter complexity is something that's related to computer science and electrical engineering, but it's primarily related to physics. And many physicists don't know this. So essentially, they have a treasure in their hands that they don't know how that it exists, and they don't know how to deal with it. So we have in organic matter complexity that ever increases as a solid. We cannot stop it. Is it against the second law of thermodynamics? Possibly it's not, because we can have a local matter complexity increase, and if we have only local complexity increase, and then we have disorganization in the rest of the universe, then overall we have an increase in thermodynamic entropy, and then there's no contradiction to the second law of thermodynamics. But then, if we have increased complexity, then where are we going to go? Is this we're going to have an explosion of complexity? Is there an end to this? Are we going to have a complexity death of the universe rather than a heat death? We don't know. And we can define complexity at both nano level, I'm going to come to this for life, but also at mega level, because the galaxies and planetary systems are organized in such a way so that they minimize gravitational energy. This means that the universe has also a complex structure, but we did not study the universe from this point of view, not yet. Now, when it comes to life, then life is a matter organization at nano level, because we talk about atoms that becomes nucleotides. Then we have RNA, DNA. We have subcellular structures, cells, organisms, swarms, colonies, and so on. So the life is organized along matter complexity. And then what's the relation between inorganic matter and organic? This means living matter. Is there just a threshold in complexity above which we have life and below which we have non-living matter, or do we have a gradual transition? Again, biologists don't have specific reply to this thing. And also, why matter complexity is so necessary for life? Why life must have a complex structure? Again, this is an issue that has been investigated. Of course, we have again the question whether complexity is just a necessary condition for life, or whether it's a sufficient condition for life as well. When we study, biologists study the transition from non-living matter to living matter, and then we have border cases that are in the transition between life and non-life. For example, prions are just malformed proteins, but they can infect other proteins. So in a sense, they replicate. And viruses, essentially, they are just protein balls that cannot replicate, but they enter into cells, and then they hijack the cell reproduction system to replicate. So are they living organisms? The biologists don't know exactly if they can put any hard limit between non-living matter and living matter, and where this this border is. Of course, if we have many living organisms, then they start interacting with each other. For example, within our mouth, we have various types of microbes and funguses as well. They interact with each other. Within our body, we have a very large number of biological processes that interact with each other, and then we need systems biology to study it, which is a science by itself. Actually, each of these transparencies, if I want to expand on this, it can become an independent lecture. It may be also an independent course. So because I bombard you with many ideas and just to have an idea of the various topics that are open for research and for discussion, and then you can continue studying some of them. And you can form your own idea, because my aim is not to dictate what I believe on you. My aim is to raise questions that you reply one way or the other, and you are knowledgeable about what's going on. And then a long time ago, Schrödinger, that was a physicist, by the way, not a biologist, gave a thermodynamic definition of life. And according to his views, life feeds on negative thermodynamic entropy. Essentially, living organisms, through homeostasis, they take as an input free energy through nutrients, for example, or through sunlight in the case of plants, and they output an equal amount of energy as heat. So every living organism, including plants, produces heat at a higher entropy level. So we have to think twice when we believe that having, let's say, more plants, it's always very good for the environment. Because, for example, if tundra expands and then the ice sheets smaller in the Antarctic and in the Arctic region, that's not necessarily good for the environment in the long run. And when, people, if we take this into account, the thermodynamic definition of life, then when we search about extraterrestrial life, this does not mean that we're going to search about for creatures that have 3 eyes, and let's say, and 4 mouths and 3 hands. It's better to try to find regions in the universe where we have low entropy matter. Then we can define, we use the information theory definition of entropy to define life. And it seems that we cannot have life without intelligence, because the entire intelligence in life is hidden within DNA and RNA that contains genome intelligence. Without it, we don't have life. Okay? And this intelligence self-replicates. So we have to have RNA, but that's not, or DNA. That's not enough. It has to self-replicate. Okay. So essentially, we can say that life is self-replicable in intelligence. And then the other question is, can we have intelligence without life? So in organic matter, for example, can it have intelligence? Depends on how you define intelligence. Maybe, advanced automatic control systems could be considered as having a certain type of intelligence. And can we have life without body? When I heard about computer viruses a long time ago, maybe 30, 40 years ago, I thought that the term computer virus was a stupid one, but it was not that stupid after all, in the sense that if we examine computer viruses, first of all, they don't have a body, they're just a piece of software, okay? But they have many characteristics that are related to life. Life has certain properties. 5 or 6 properties. I don't remember the exact number. For example, life has organization. It is stable when it receives inputs from the environment. it can replicate and it can die, of course. Viruses have all of this, but metabolism and growth. They don't grow and they don't have metabolism. The viruses, the computer viruses, as they are right now. Well, now what's the relation between AI and complexity? AI is our effort to mimic human intelligence in understanding the environment, in interacting with the environment, and nowadays also we use AI to build new worlds, to build new images, new videos that, according to their social use, can be either deep arts or they can be misinformation or disinformation. So essentially creative fraud. AI has traditional two approaches, classical symbolic AI that failed to deliver, and machine learning that at the beginning it was discredited back in the 1970s, 80s, but then it took over, and nowadays when we say that we talk about AI, essentially we talk about machine learning. And machine learning operates on data. We need data to feed the machine learning algorithms, to train DNNs to recognize, let's say, facial images. And what are these data? Data are essentially numbers, okay? And we organize numbers into vectors. Essentially, vectors are just series of numbers to say it in a simple way. Once we do this, for example, let's say we have humans and we measure we weigh them, and then we measure the height of a human, and then we represent each human by its weight and its height. And if this is enough for our job, then we can forget about humans, we can forget about the reality, we can live in the so-called vectorial spaces in mathematics. Essentially, we live in a world of numbers. And this is what machine learning does, and it's not only machine learning that does this thing these days. Data analysis is used in all sciences, and essentially every science, including the liberal ones, the liberal studies, are mathematized. And this is a very big issue related to education these days, whether we can do it or not. Some of these data have a spatio-temporal structure. For example, if we have the time series of euro versus US dollar conversion rate, then we have a series of numbers that can be easily represented by a vector. Or when we have an image is just a series of pixels, and again, we can represent an image by a vector. But these vectors, they don't have 2-3 dimensions as you typically know. They can have millions of dimensions. For mathematics, that's the same thing. Whether we have a vector of 2 dimensions or a vector of 10 million dimensions, the mathematics are more or less the same. And we have an exponential data increase. Why these days? So we live in a world of data. And why is it so? First of all, because the world complexity increases. We produce ourselves data out of our own activities in finances, for example. The complexity of our buildings and cities increases, so the data that come out of them also increase, and also the sensors that we have to get data from the environment. Also, they skyrocket. Every one of us has a mobile phone. Mobile phone produces digital audio. It produces images. That's all data. So we live in a society of data, but we don't live in a society of knowledge, because if you define knowledge increase, let's say, by the number of publications that you get per year, then nowadays the increase is linear. So we have an exponential data increase, but only a linear knowledge increase. Why we need more data? If we want to understand a more complex world, then you need more data, and you need data analytics. And can you do it as a human? Humans cannot deal with so many data anymore. So you need machines, and you need AI, and in more generally speaking, you need data analysis. Artificial intelligence is just one way to do data analysis these days, and it's very popular. So essentially, in this sense, AI is our reply to the complexity of the world. But at the same time, it increases the complexity itself, and this creates other problems I'm going to talk about. In case of AI, then we have a number of things that we can do. Each image can be represented by a vector. For example, this vector here represents images from Ioana. This is my secretary. And this vector here represents images of Sotiris. And we can have many such vectors related to Ioana and many such vectors related to Sotiris. They group with each other, and then we have clustering. And this way, instead of having thousands of images of Ioana and thousands of images of Sotiris, we can just have one of them here and one of them there, and we do data compression. Our brain does data compression as well, because we don't store everything that we see. And also we can have abstraction in the sense that nowadays, once I have done clustering, then I can put the label Ioana here and the label Sotiris here. And then this is how I create concepts. There are another issue is supervised machine learning, where we have data points. For example, here can be data points related to the weight and height of, let's say, men, and the weight and height of women here, and you want to separate them somehow. You want to find such separating surface. How are you going to define the separate surface? It's just such a relation. So this is, let's say, the input vector, weight and height, two numbers. These are parameters that I don't know that describe this separating surface, and the output is 0 for a, let's say, for a man and 1 for a woman. Okay. So basically, what I try to do is I try to find the parameters. This means I try to find the separating surface out of a number. I measure weight and height for 1,000, let's say, men and another 1,000 women. And this is my training data set, and I try to find a function that separates the two. Or here it can be images of mine, and there can be images of Andrea, for example. Again, we have, let's say, hundreds of such images, and we try to find the separating surface. That's the same thing. So now once you know this relation here, basically you're done with machine learning. And this is something that people cannot really grasp, but an entire course, a full semester course on machine learning, just tells you exactly this thing. And of course, then it specifies various mathematical ways through which you find this function here. But essentially, what AI does these days, including ChatGPT and all other very nice things, they just work with such functions. So if you think that ChatGPT is just such a function, then you're not afraid of ChatGPT anymore. It's mathematics. Maybe you don't understand them. But if you study them, then you're going to understand them. There's no need to be afraid of them. And after all, even if you're afraid of it, then what's the use of your phobia? Is it going to lead you anywhere? I don't think so. Another thing that we do these days is we try to find the probability distribution of data. Let's suppose that somebody takes 1,000 images of mine. X is just an image of mine, and I have 1,000 such images, and then I calculate the probability distribution of my images. This can be done. There's no need to go into mathematics how this can be done. But let's suppose now that I have found the probability distribution of my images. Then I go to this probability distribution and I take one new sample and I show this to you. So you see a new image that is PITAS-like, but it does not exist in reality. It's fake data. It's a fake image. But the better I approximate this probability distribution, the more realistic, the more PITAS-like this image is. Okay, and this is how we work in generative AI these days. And depending on the social use of the new images that we create, they can be fake images that can be used for disinformation, or they can be art. Okay? Exactly the same technology can be used for two different social purposes. Now, as I've told you, the human brain works in a different way. It's not working exactly like machine learning. It is based on concepts and ideas. For example, we have instances of a triangle, and then we have a definition of what's a triangle. And this is how we work, and we do reasoning on them. And we try to mimic this thing using symbolic AI and mathematical logic, but it didn't deliver. Because reasoning, human reasoning, is one very complex brain activity. Even nowadays, we don't know how to do this properly. The machine works in a different way. It cannot mimic well human reasoning. Not even the most advanced LLMs that we have these days. And actually, right now, when we talk about AI, this means machine learning, this means deep neural networks, and we can continue advancing this way, but that's not enough, because this is not the way the human brain works. If we really want to mimic the way human brain works, then we have to fuse machine learning with symbolic AI. We're not there yet. Maybe through LLMs, we can start learning how to do this, but it's not obvious how this can be done. And it's going to be a major breakthrough, of course, if we go to this. Now, what are the artificial neural networks? They try to mimic human neurons in a static way. So essentially, we have some input numbers here. We multiply them with some weights. We get it through a nonlinearity, and that's an artificial neuron. But one of them is not good enough to solve your problems. You need a number of those artificial neurons organized in a structure, a multi-layer artificial neural network, which has a certain resemblance to the biological neural networks, because the human brain, we have millions of neurons with trillions of synapses. This means points of contact between two neurons, and both of them are complex networks. This is a complex network, very complex network actually, and this is a complex network as well. It's fairly regular, but it has certain complexity. We don't know how to measure complexity, neither in biological neural networks nor in artificial neural networks, and even now we don't have a proper reply on what a neural network knows, an artificial neural network knows. So if you have a neural network, you trained it to do facial recognition, and you want to know exactly what this neuron does, there is no definition of what is artificial neural network knowledge. And using such as the artificial neural networks, again, you see we have the same relation here. X could be an input facial image of mine. W is the parameters that have been trained through thousands of images or millions of images if we want to have a neural network that recognizes thousands of people. And then we have the output here that gives, let's say, value 1 for me, if it's my image, and value 0 for the rest of you. Okay? And this is what essentially machine learning does these days. Of course, as I've told you, we can model the distribution of our data, and this leads to generative AI. We can model, for example, how these video data are distributed, and then we can resample it and create such a new data, which is a new video, which is completely new information. So this information did not exist in the past. It was created through generative AI tools, and it's now part of a new reality. So essentially, we use AI to increase our reality. And we're only at the start in this respect. And one of the ways one of the things that we create is text, and this is what is done with the large language models, ChatGPT, for example, these days. Essentially, transformers, which is a type of neural network, tries to understand the statistical relations between words and their position in a text corpus. And once it learns all these things well, then it can output new text that did not exist in the past, that is relatively smooth. That's the basic thing of LLMs, and they are very good at this. And many people that interact with them think that they are humans, because they produce good output, okay? And this is dangerous. And again, they have been around only for how many now? 4 years, less than 4 years. So we're still at the start. They don't think, they don't feel, but they can cheat you to think that they think and they feel, okay? And maybe, in the future, they can start thinking as well, because they can be used to bridge the gap between symbolic AI and machine learning. We're not there yet, but there are steps towards this direction. Well, now what about society? Society is humans that interact with each other. Here we have a friendship relation in graph, in social networks. So essentially, the societies can be described by graphs, and we can use graph theory to analyze societal processes and social network processes. We extensively do this for social networks because we have huge amount of data, not me, but Meta has huge amounts of data that can be analyzed using linear algebra, for example, and graph theory. And then you see that there are certain relations and analogies between neural networks and social processes. Here, for example, in direct democracy, we have some people, they take the decisions. So it's just like having a one-layer network. If you have representative democracy, as most democracies are representative these days, then you have people that vote for deputies, and these deputies form the parliament. So you have a multi-layer structure that looks like a multi-layer ANN. Maybe this network, this structure, representative democracy, has more layers, and this means it has bigger capacity to store knowledge, and maybe it's more stable. But all these things are just conjectures. You have to study these things, and hopefully you can get a better understanding in a mathematical way on why representative democracies work well, or work better, possibly, than direct democracy. Because nowadays many people think, let's use social media to have direct democracy. Is this the solution? It's not clear whether this is the way to go or not. It has to be studied. And we can study new political theories based on the new tools that we have, and maybe we can come up with other structures that are democratic and they are better than the representative democracy that we have now. Maybe. Because our current political system is already 300 years old. So basically from the 16th century, the English Parliament and the French Revolution, we don't have much of a change. And if we want to come back to reality, we see that nowadays AI and information technology, they are not only used to understand our society, they can be used to change our society. And this is social engineering. Propaganda was social engineering mechanism a long time ago, even in the time of Nazis, for example, and so on. But nowadays, this is done at a massive scale and using exact AI and information technology tools. And essentially, it's like going to Marx's 11 Theses on Feuerbach. So we don't only interpret the world nowadays, we change the world as well. Of course, Marx said this in a completely different context, but that's what we do nowadays. We use AI not only to understand the world, but also to change it. For example, if I go and micro-target each of you with specific personalized political advertisements, then this is already influencing the electoral processes. And this is what happens these days. It's not theory. It's a real danger for democracy. If I start spreading false information around, then essentially I falsify your right to be informed. And without this right, you cannot judge well. Again, it's a threat to democracy. Now let's go to the environment. Well, again, in the environment, we have things that are interact with each other. For example, in a forest, trees interact with each other through funguses, and they create a whole biosphere. And this biosphere that encompasses all living organisms has huge energy needs. We know this. It produces high entropy heat, because it gets solar energy, let's say, and then this is transformed into high entropy heat that goes to the environment and has to be sent out by radiation in the night by the Earth. If this is hindered, then we have trouble. Of course, it's good that plants, through photosynthesis, reduce the CO2, and then we don't have the CO2 blocking, or methane blocking the radiation of the high entropy heat to the universe. And then we have what I would call anthroposphere, which is essentially humans and man-made environment. And we have a very high complex structure of whatever we do these days. We have megacities with extremely complicated structures. Just to create them, we need a lot of energy. And to maintain them, we need even more energy. And the question is whether this is viable in the future. As I've told you, the complexity increases, and it increases in unforeseen ways in the following sense. When I have a problem, I have a disaster, for example, I have a flood somewhere, then I start building dams, I start building other constructions. Essentially, I increase the complexity of the environment even further. But then we are in a vicious circle. So we have increased complexity that creates natural disasters. You increase the complexity to counter this, and then you have a positive feedback loop, which is bad. It's unmanageable. And of course, we have global population growth. We're still in the steep slope. We have an increase of the global population. All countries try to have a certain level of increase of their GDP because they want to become richer. And this is why we need huge amounts of energy. Actually, we need about 17 terawatt power, which is 10 times less the total, 10,000 times less the total solar power that arrives there. But so you can say that it's peanuts. We get so much energy from sun, but that's not. This is not good enough, because we need free energy to feed the population and to build and maintain the whatever we do. And then we don't have that much free energy available anymore, because we don't. We should not speak about the total solar power. We should speak about the free solar power that's available to us. Luckily, if we use renewable energies, then their cost drops. So instead of using oil and gas that produce CO2, we can use renewable energy. This is better. But the question is how can you organize this renewable energy production and distribution? It's not easy. Hopefully, if you use AI technologies, you can have better, you can have optimization both in energy production and in energy distribution. So AI could provide the tools for a solution, but right now AI is part of the problem, because AI, the way it's developed nowadays, it's energy hungry. So instead of AI being part of the solution, at this point, AI is part of the problem. And this is a big issue. And we cannot continue working this way. We cannot continue relying only on big AI factors and big data centers. This is one way to have intelligence, but think about humans. Human brain, it's much smaller. It has a high intelligence capacity, and yet its energy needs are small. We eat about 3,000 calories per day. That's peanuts compared to what was the energy need for an AI factory. So there's in between. There is a big spectrum of technologies to be investigated, and have green AI, let's say, technologies. So we have an increased complexity of anthroposphere. This leads to even bigger energy consumption. And then the question is, can we model this? Yes, we can model it. We can say that we are going to have this global population growth. Our aim is to have this GDP growth level, and this is our capacity to use new technologies like AI for a better efficiency of our society, and put them into a mathematical model. And then this can be done, and it's not that complicated model. And then if you create this model, you can check whether there is a feasible solution. Feasible solution is that you find the condition that you can say that if I have a population growth by 1% and zero growth in GDP, and I use a new technology with those energy characteristics, then this is doable. Or you cannot find a solution. This means that the only way out is destruction, because one way to solve problems is to destruct them through wars, through environmental destruction. Death is a way to get out of this. Of course, this is not something that we would like to see, but it's a solution in principle. So now we have, when it comes to environment, the Earth is an open thermodynamic system, because we get solar radiation, and then this is low entropy energy. It's converted into chemical, kinetic, and thermal energy, and then this creates high entropy heat. That it's a heat waste that it's emitted to the universe through the heat surface. And if this works well, then we're in a stable situation. If we don't, if we disturb this cycle, then we're in trouble. And why are we in trouble? Because through life and through what we do, we create order. By creating order, we reduce entropy, but this is against the second thermodynamic law. Somewhere else in our environment, we have increased entropy. Increased entropy means increased randomness and increased instability. And this means that due to this instability, we're going to have more mega fires and more mega floods and other such events in the future. So we are in a vicious circle that somehow we have to regulate, and we don't know how to regulate it well. And there are some ideas that are, let's say, proposed as a solution. For example, politicians say, let's use nuclear energy, okay? Nuclear energy doesn't produce CO2, so we're on the safe side. That's not true, because nuclear energy produces high entropy heat waste that is going to create sooner or later the same and even bigger problem. So we have to think what we're doing. As I've told you, if we expand tundra and we reduce the albedo of the Earth because the ice is becomes smaller, then this is something that is not good. And we don't know how to model the environment. We don't have precise environmental models so far. I already told you about the excessive heat waste production. We have, as I've told you, a positive feedback loop between environment complexity, instability, and human response that we don't know how to regulate. We have to break this positive feedback loop. This means that we have to model our environment better and predict it better. This means that we have to invest in science, in environmental science, and we see the opposite things happening these days. In the US, for example, we have a big reduction of money that goes to those types of studies. AI is good in mega disaster management. I'm going to come to this. And so we can see how we can possibly use AI to provide solution to some of our problems. For example, as I've told you already, we can use AI for optimal energy production management, optimal energy distribution, and so on. We're not there yet, though there are ideas how to do this. We model the environment nowadays in a better way using neural networks. In the past, modeling the weather systems was done through fluid dynamics and differential equations. Nowadays, it seems that physics-informed neural networks, they produce better results for weather prediction. And I'm going to come to this. AI is good is mega disaster management. So there is a hope. So now let's go to the natural disasters and how we deal with them. This research has been funded by the so-called TEMA project by the European Union. It's a big project with 19 partners, 12 million euros as a budget. And over there, what we do is the following. We have data sources for natural disasters, wildfires and floods. We have satellites, we have drones, we have meteorological data. We have social media data because nowadays people, especially if they are in danger, tend to send messages, take pictures, and this is information that we can use. We do big data analytics. So we try to detect humans in danger. We try to find the extent of a flood by flood segmentation, and then we send this information to physics to phenomenon modeling. We model forest fire or we model flood, and then we present all of these results to the civil protection authorities and the firefighters for better management of the event. So that's what we do in this project. We can use a number of sources. For example, we can use infrared and visible cameras to monitor a forest fire. We use drones with proper sensors to fly over an event and collect data with high detail. We can use satellite images if they're available. Some countries are well covered through satellites, others not so much. Then we can use deep neural networks to do fire segmentation. For example, here we segment the fire regions. Here we segment both the fire regions and also the smoke. And sometimes smokes create problems because you cannot see through smoke infrared in visible images, so you have to use infrared imaging to spot the flame areas. And then we have tools for forest fire modeling. Here, for example, that was the epicenter at the start of the fire. The wind was flowing this way. This is an event that has happened a couple of years ago in Sardinia, in Italy, and this is the expected, the modeled evolution of this forest fire. It was a big forest fire, devastating one in Sardinia. And then if you have burnt regions, you have to find which is the extent of the burnt regions, which is the damage. This is also something that we do. When it comes to floods, it's a good idea to detect humans and cars that are possibly half submerged because they're in danger. And then firefighters know that in this particular case, there are many people that have been trapped, so they have to react. We do flood region segmentation, again, using neural networks because we want to know the extent of the flooded area. And we do the same also at a bigger scale using satellite images. DLR, that's the German Aerospace Agency, has done some analysis of a big flood that we had in Greece 2 years ago. That was really a mega flood. So we use any type of data source that's available, we analyze it, and then we fuse the analysis results. So we take all the information together. When it comes to floods, then we do flood modeling. NS is a Dutch partner in this project that has software to do flood modeling, and we feed it with proper image data and meteorological data to this end. Sometimes it's a good idea to have digital twins of the environment because the 3D terrain model is important for modeling floods, for example. So this is why we fly drones over the city of Larissa in Greece that was flooded. And this is the 3D twin model that was created. As I've told you, we analyze also geosocial media. We analyze tweets and we check whether we do sentiment analysis on those tweets, and we can check whether a group of people is just afraid or if they are in panic, for example. And then the firefighters have to respond to this problem. So this is the TEMA consortium. We have among us University of Seville in Spain that does drone image acquisition, and also the Tecnosilva is a Spanish company that does fire simulations. I think that they have applications in Chile and in Argentina as well. So that's all. If you want to, as you see, my talk had 2 parts. The first part was more philosophical and epistemological. The second part was more technical, though at a very high level. If you're interested in the philosophical part of AI, then I have authored a book back in 2023. And that book at the time was prophetic in the sense that back in 2022, when I was authoring the book, metaverse, for example, was a big thing. but it failed, and I predicted that it would fail. At that time, nobody was talking about the danger of social media, but I have predicted that social media can create a very big problem to vulnerable people, like to the minors, and now this has been manifested, and there are governments that try to address this issue. So do you want me to say a few things about AIDA and then have questions, or? So?
Maybe someone wants to ask something about the presentation. ¿Alguien quiere hacer una pregunta? No sé si
Okay, and then I'm going to say a few things about AIDA.
Hay que utilizar el micrófono para que la gente del Zoom nos pueda escuchar.
No, estábamos diciendo que si alguien quiere hacer alguna pregunta sobre la presentación del profesor, pueden escribirla por Zoom, si es posible en inglés. Y nada, y acá los presentes también, si quieren hacer alguna pregunta, sí, le podemos consultar. Luego el profesor va a continuar explicando sobre AIDA. Yo tengo una pregunta. You mentioned that AI development requires enormous energy consumption. What concrete advances are being made in development of green AI? Are there already neural networks architecture that achieve an effective balance between energy efficiency and processing capacity?
First of all, right now we are in the wrong course of developing AI, because the way we develop AI nowadays is power hungry. And the reason we do this is because some big companies like OpenAI, they have huge funds, and it's easy for them to build very big data centers and very big. They have the money to do this. Okay. But then already the consumption of energy consumption for AI development skyrockets, and this is clearly non-sustainable. That's thing number one. Thing number two is that this is not the only way to do AI. And DeepSeek it was a big surprise for big American companies, because they have proven that they can create more efficient models. There is a whole line of research on green AI, how you can create smaller models that have good capacity, less energy needs. But this is not the main. This is not one of the main research avenues these days, because big companies continue working their own way. And this is bad for them. This is bad for us, because if they continue this way, then we're going to enter into a financial crisis, and it's going to hurt all of us, not only them. And then we see that there is a very big gap in terms of energy efficiency of the human brain and the current AI machines that we have. So we have to think to research and build technologies along this line between the two opposites, human intelligence and current artificial intelligence. And there is much room for development there, and it's a very good research topic also for younger scientists. And it's going to be a very valuable contribution to the AI science, in my view.
Thank you.
¿Te puede preguntar?
Sí.
El chat está deshabilitado, no sé si alguien me escucha.
Sí, se escucha. Sí, se escucha.
Sí, se escucha bien.
Bueno, trato de hacer la pregunta en inglés porque el chat está deshabilitado para todos, así que, bueno, si se me escucha, pregunto.
Sí, se escucha perfecto.
Okay, first of all, thanks for the really nice talk, Professor. I want to ask about the disaster detection models. Do they use time series data to predict?
Excuse me, to predict what?
To predict, I think they are predicting something. No, when you talk about you are trying to prevent a disaster. So I think you are trying to take a rate event to happen.
Things for modeling and forecasting a disaster. One is the classical modeling tools that have been developed for some years now, both for forest fires and for floods. So far, we use the existing tools of these two companies, that Tecnosilva and NS, and we just feed them with better data. And we do it in a faster way. So we receive data, we analyze them, and for example, we detect where the fire front actually is right now, and then we send these coordinates to the fire modeling software, and then it does a better prediction. So essentially, using neural networks, we don't do prediction. We analyze the data and we feed the models that do the prediction. So it's a two-step approach. But many other things, of course, can be done there. This is not the only way that we operate. By the way, regarding physics modeling, the models that we currently use, for example, for forest fires, are not good enough. Because, typically a forest fire gets stronger if we have stronger winds, okay? And this is what the Tecnosilva software does as well. But it seems that in the recent years, in mega fires, we have a different situation. We have the so-called pyrocumulus situation, where the forest fire is so big that it uses its own climate, its own winds, and then you have a fast evolution of the forest fire without external wind. And the software models that we have so far for forest fires don't work well on mega forest fires. So we need new models for these new mega events that we have. And the reason we're not there yet is because they don't have enough data. So this is a fairly new event. It's difficult to fly around such mega fires. It's difficult to collect data. And if you don't have data, then how can you model the situation?
Okay, thank you.
You're welcome.
Que sería más predecible que el incendio, que en inglés no es lo que se nos
Buenas, no, que estaba hablando de los incendios, pero sería más factible las inundaciones, serían más predecibles que los incendios.
So can you translate, please? Better use the microphone so that the others can hear you.
She asked if the floods are more predictable than fires.
No,
Are the same.
It depends on the type of floods, because there are regional floods when the waters rise slowly and you have time to model them properly. But then you have also flash floods when there is a very strong downpour of water. So within 2 hours, it rains as much as 1 year in some cases in Greece. Then you have streams that start, bursting with water, and then it's difficult. You don't have enough time to react. You don't have enough time to model. You need actually very good weather predictions for the events. It's not enough to have a good general prediction on what weather is going to be in Greece at that period. You need specialized meteorological information for certain regions that are in danger. Typically, these forecasts are not good enough because forecasts are done at a grid which is it's very sparse. So we're now trying this project in Project Tema to improve the weather forecasts for flood modeling by using also local measurements. So we get the general meteorological predictions, we fine-tune them using neural networks with local data measurements, hoping that we're going to be more accurate on the precipitation for particular cases. But they can be very dangerous as well. I mean, flash floods.
A veces depende de la región también o cómo llega la inundación a la ciudad.
She says that it depends of the region or how the water arrives to the city.
Yeah, definitely. It depends on the three terrain. That's why we create 3D terrain models. Particularly in Greece, we know that there are 4 or 5 regions that are prone to floods because they receive weather fronts with lots of precipitation, and the rivers that flow out of them, they are very small. So we try to do good modeling. First of all, 3D modeling of the terrain of these regions, and also good meteorological predictions for them. So we concentrate on those regions. This is natural.
Acá en Calafate frontal, por ejemplo, y en Corriento más al norte es como que hace inundaciones, pero alrededor va haciendo en contorno. Y acá dice el de frente tenemos a Calafate solamente. Se lo corto. Sí, en Calafate tenemos solo inundación, sería de frente. Si viene de Calafate tenemos una sola área para cubrir que viene desde la costa a la ciudad. En otras regiones es como que hace el contorno en la ciudad.
She said that in Calafate they only have one friend, but in other regions they have around like Greek.
Well, maybe there could be a cooperation between your universities and Tema project towards using these technologies, and then you can apply to particular locations here in Argentina, if this is of interest to you.
En Argentina más complejo para hacer las teorías.
She says that it's more difficult in Argentina to make the theory. But
yes, but things have to be done.
It depends. Thank you very much. No sé si hay alguna pregunta.
I'm here to reply to your question.
Thank you for all your presentation. It's a pleasure to meet you, to hear you. I'm very worried about teenagers and all these kind of things. especially with artificial intelligence. And I would like to know if there are any studies about the negative effects that artificial intelligence causes to adolescents or children, young people.
There are already studies that show that there are negative effects if the use of social media and also AI is uncontrolled in many different ways. And the important thing that I try to point out also 4 years ago is that it's not only young people that are in danger. Every person that has a relatively weak character or has other social problems or psychological problems, she or he is vulnerable as well. So we have to do things. The question is what to do. And then the reply is not clear. We have the example of Australia that banned the social media use for persons up to 15 years old. I think many European countries go along this direction as well. Whether it's going to work or not, who knows? To me, the excessive social media use, it's like drug use or alcohol use. So you can say that by banning drugs or banning alcohol, you don't solve the problem. And maybe this is going to be the same with social media. We don't have figures on how efficient a ban would be. Maybe, in Australia, after 1 or 2 years from now, we're going to have numbers. Maybe. And there were cases that I think in South Korea had some numbers that were not consistent. So we know that we have to do something, but we don't know what we should do.
Do you think that schools have to motivate the use of artificial intelligence?
Now, that's another big story. There are two big problems there. First problem is that AI is not ChatGPT only, okay? So because many governments and many students think that AI is ChatGPT. So essentially, nowadays, all students, high school students, they should learn the basics of AI. They should understand what's data. They should understand how we use data to do machine learning. So it's like a branch of mathematics. So we have to rethink how we teach mathematics and computer science so that everybody knows the basics, because the basics are going to be here not only for today, but for, let's say, after 10 years or after 20 years, because mathematics don't change that fast. And many governments don't understand this. And they think that if they start, using ChatGPT in education and start educating, using it to teach students, it's good enough because they can personalize education, or they can lower the costs of education, particularly in sparsely populated countries like Argentina. Well, we don't actually know what's going to happen, because students need the notion of a class. Learning within a class is one thing. Learning by yourself, it's another thing. It's okay for older people, that do it for continuing education. That's okay. But if you want to substitute the class education with personalized education, it may have disastrous effects on students. And also, the way you're going to use these models, it has to be done with we have to study how to do this, because if we overdo this, then students are going to start not using their critical thinking, and then this is going to be already bad. We have already such examples. For example, Sweden, they pioneered about 10 or 20 years ago the use of electronic means for teaching, and then they found out that by using them, actually it was bad for their kids, and now they go back to classical books. So but this means that 10 years of education have been lost, and was bad for the students that were studying at that time. Actually, right now, we have two education paradigms that can be used. One is an expensive education system where some well-qualified professors work with few students in a very small class, and then they use also AI and all these tools, but under supervision. But this costs a lot. It's a huge cost. And then the other way of doing things is to have mass education, remote learning with in a personalized manner with AI tutors, and that's for the masses. And for me, this is a bad evolution if it is left unregulated, because it can have exactly the opposite effect to the one that's intended. So, and after all, having an elite that's very well educated because they can afford to pay it, and then masses that are they're not well educated, this is a recipe for disaster. It's a recipe to go towards totalitarian regimes, towards technophobia, and towards, after all, you know, I've told you that right now we are in a data society, okay? Are we going to transition into knowledge society, and how can we transition to knowledge society? If we have knowledge increases now linearly, possibly it's going to increase exponentially in the future. So how the humanity can increase this knowledge? How we can transfer this knowledge from the current generation to the future generation? If the masses are not well educated, they cannot do this. And we had such problems in the past. At the end of the ancient times, we had the ancient knowledge, Roman and Greek culture and so on, and it did not pass to the future generations around the around the 6th century after Christ, for various reasons, because of population migration, because of Christianity, that at that time, you know, they had a very bad attitude towards ancient knowledge. The ancient knowledge did not pass to the new generation. Then we had 1,000 years of dark ages in the medieval times. So there is a real risk that if we don't do education properly now, to enter into such a phase. It's a real danger.
Hi, Professor. Nice to meet you. Do you think the hydrogen energy is the future, or this energy have a defect?
I did not understand the question.
Okay. He's trying to know if. What do you think about hydrogen? Hydrogen, I don't know. Hydrogen. Ahí está.
If hydrogen?
Green energy, yes, as a green energy.
Well, hydrogen is a way to store green energy. I'm not an energy expert, but I know that when you have excessive solar energy, let's say, there are two ways to deal with this. One, when Europe has daytime, is to send energy to America that has nighttime. This means very efficient energy grids for transportation. We're not there yet, not even within Europe. And the second solution is to store this energy. Then you need batteries, or one way is to transform this excessive green energy into hydrogen. It's a mean of storage. of this energy. Whether it's a good solution or not, I don't know. I know that it's so far there are experimentations, but they have problems because it's a dangerous material, and they still work on this. But I'm not expert.
Mr. Pitas, someone is asking, connected by Zoom. Soledad Caracoche, she said, thanks for everything. Are you modeling the glacier retreat in South America and its consequences for local population and impacts on ecosystems? Thank you very much.
You can. This is the same that I've told you before. You can a university here can use our system to do exactly this thing, to monitor, for example, how glaciers retreat, and then you use two types of information at least. You use satellite images, but you fly also drones, collect local data as well, and then do proper modeling of glacier evolution. This is doable, but somebody has to do it, like your university, for example. And that's why I'm here, so to check whether there are possibilities for such cooperation. Thank you very much.
Πάρα πολύ είσαστε εδώ μαζί μας και να ξέρω ρωτήσω κάτι. You said about data that you need to collect. From where are you getting that data to the models? For example, here in Argentina, the scientific investigation, it's extremely poor, extremely poor. And when we have the opportunity to do scientific investigation in general, is coming from abroad, Japan, Europe, Deutschland, I don't know, and other countries, not from our country. That's very sad. So those models that you have are using which data information? Are you taking papers from specific universities around the world? From where are you collecting the data? That's my question for the different models you are using for forecast, I don't know. Disaster, for example, meteorological disaster.
So first of all, regarding the methods and technologies, you can always use what other countries produce. In Greece, for example, we use also technologies that come out of TEMA, and as you see, TEMA technologies come from Spain, from Netherlands, from Germany as well. So we try to use such technology and develop our own. I think that you can do the same as well, provided that somehow you have proper research funding, either through national sources or through international cooperation. You can participate in EU-funded research, for example. I think that Argentina is an associate member of Horizon Europe, so you can participate in such projects and get funding. And this somehow solves the problem on how to get know-how and technology to solve your problems. Now, when it comes to data, then you're a big country and you produce data anyway, no matter what. Because your economy, produces financial figures if you want to model your data exists here. Now, whether these data are collected properly, whether they are curated properly, whether they are accessible by the Argentine researchers, that's another story. But definitely, you do have data. In specific cases, when you want to study glaciers, for example, glacier evolution, then data collection should be specific. Either you find them from satellites, and I don't know if they are for free or if you have to pay for them, or you can then have to have local measurements. That specialized scientists do this, but then this costs. So again, this boils down again to research funding. So you need funds, research funds, and you need accessibility to data. That's my feeling.
Haristo. And another question is about related with what she was asking. Conscious in artificial intelligence, how do you think we can measure that the artificial intelligence be accurate and conscious? Wrong information. That's my main concern nowadays about artificial intelligence. For example, if that models are taking accurate scientific data, because nowadays we don't know what's true and what's not true about artificial intelligence and with what kind of data we're feeding ourselves.
So your question is actually 3 or 4 different questions. Let's get things one by one. First of all, regarding consciousness, as you understand, AI was not meant to have any consciousness, and it does not have any consciousness. At least the way we think about human consciousness. The problem is that with human consciousness, is it possible to close this window, please? The problem with human consciousness is that we don't know exactly what it is because human consciousness, has not been studied properly in psychology. So once you don't know what human consciousness is, then how can you judge whether a big system can start it having elements of consciousness? Nevertheless, so far, all indications are that AI does not have any consciousness, but this is only part of the story, because if somebody accesses such an AI system remotely and thinks that this system has consciousness, this is already something different and it's problematic. And there are many people that they get attached to AI systems, and because they think that they are intelligent, that they are extroverted, they even want to marry them. But this is related to the social use of such systems, and at least people should know when they talk to a machine or when we talk to a human. So each AI system should have an identity, and when you talk to it, then you should at least know that explicitly that this is a machine. Now, regarding accuracy, there are many things that affect the accuracy of an AI system. Generally speaking, scientists try to do their best to have as accurate AI systems as possible. Of course, if your data are not accurate, if they are noisy, then this has an impact on the inference quality of your AI system. And for example, you can have bias. If your data are biased, that, for example, all black people are criminals, then this is reflected to the quality of the AI system. But this is not a problem of the AI system itself. It's the problem of the data that you use to train the system. So you have to be very careful on what type of data you use for training the AI systems. And so far, big companies like OpenAI, they don't care that much about it. They just grab information from internet, wherever they find it, without it's for such huge amounts of data, you cannot really do quality checks, and they're just happy with whatever their systems learn. So sometimes if they learn Nazi ideology, it's a bad byproduct for them. And such things happened. Thanks for your presentation. They better use the microphone.
Hi, and thanks for your presentation. Can I ask about the quantum computer, if it's going to be a game changer about AI? What do you think about? Or it's too soon?
Quantum computing is still at an experimental level. There are high hopes that it can be used for machine learning as well, but so far it's early to say what's going to happen. Most promises about quantum computing are related to cryptography and other problems. If they're available, then we can start using them. There are ideas on how to use it for machine learning, but
now
it is in the calendar now, but it's quite soon to have to have concrete results on this.
Okay. Another question, please. What about the data centers that are talking about to make in orbit? Is that possible or not?
Sure, it is possible. Why not? I mean, you can, if you can fly such satellites that have strong computing capabilities, they're going to be a little bit heavy. But if you leave them up there, then you solve quite a few problems this way. Yeah, this is doable.
Okay, thank you very much.
There is no more question. No hay más preguntas.
Then I can say a few words about the National AI Doctoral Academy.
Please,
As I told you, one of the big issues that we have these days is about AI education. And this applies to all levels, from high school to university education to doctoral education. So the AI Doctoral Academy tries to coordinate AI education at master's and PhD level and postdoc level in Europe. We have 60 universities so far, 61 actually. Now UMPA is one of the members of IDA, and also we have a university in the US as well that participates in IDA. We have also very good R&D centers and companies that participate. And we organize short courses, and we open up our short courses to short courses of other universities. For example, an UMPA student can participate in a short course that we offer in Thessaloniki. Usually this is done through teleeducation. We have organized so far about more than 100 IDA courses and 14 summer schools, and we delivered also top quality AI excellence lectures. Overall, about more than 10,000 people from all over the world participated in those events. And if you want to participate in such a short course, there's no need for your university to be a member of IDA. No matter if a student is in India or in Argentina or in Spain, they can always register to these courses. Some of these courses most of them are for free. Some of them are for a fee. So you can always go there and register. And besides this, the AI excellence lectures, they are very well attended. They are always given by top scientists all over the world, and they are for free. So they are always for free. And besides this, we started also collecting educational resources. We have about 400 educational resources, data sets, publications, videos. You can go there and get them. And we also organize symposia on AI education. The last one, the first one, took place in Greece last summer with 300 participants, and now the next one is organized in Hungary. So if you want, you can organize such an event in Latin America. So this is double. Yeah, okay. So that's so regarding IDA, there are two options. One is to participate in AIDA as a member. This means that an institution member. This means that your rector is willing to sign the accession papers so that your university becomes member of AIDA. This is one possibility. Second possibility is that you participate in AIDA events at a personal capacity. If you're a student, you participate in an AIDA short course. If you are an AI professor and you want to offer an AIDA short course, you can also offer such short course. We have mechanisms to have external lecturers offering AIDA courses. And the aim is to have quality AI education because we need many well-educated AI scientists, and the more we have, the better. So that's all about that.
A question. For AIDA member universities, are there mechanisms for joint research project or doctoral student mobility between institutions?
So far, we did not have AIDA mechanisms for exchanges, student exchanges, because there were other mechanisms that have been implemented in the European Union for such exchange. So there was no reason to have one more exchange mechanism. But we are thinking about it to have such possible exchange mechanisms, because it's always good, for young people to come in Europe, or European students to come here and have exchange of ideas. It's personal contact. It's always very good.
Yes, that's true. Thank you.
You're welcome.
¿Otra pregunta? No sé si la gente que está por Zoom quiere hacer alguna pregunta sobre AIDA. Bueno, thank you very much y le damos un gran aplauso al profesor.
Thank you very much.